Hi everyone, welcome to our 8th lecture. This lecture is going to be on voltage, current, and resistance, and it's a combined lecture for both the calc and non-calc based physics students. It's the second in a series of lectures on electricity and magnetism, and it was actually recorded last year at this time, but again, I had to remove that introduction because it doesn't apply to you this year. Okay. What I did last time was just a general theory of electricity, mostly electricity, okay? And, when we talked about, the electrical force and electrical potential and so on, we didn't really talk about, in what sort of a situation it occurred. In fact, implicitly in the background was the idea that we were talking about electric field and electric potential in a vacuum. Okay, and in fact, the last example I did where I had this electron accelerating between two parallel plates, the assumption was that this was in a vacuum, okay? And, like in cathode ray tubes, which were the old style television sets, they actually were a big tube. And this tube was a vacuum and, electrons were accelerated in there. But mostly, the flow of electrons occurs within matter. Okay, and it usually occurs within some kind of a circuit within matter, and so we tend to call that electronics. But I don't want you to think of this as basically like electronics, like that you would go into a lab and just hook up resistors and capacitors and batteries together. This actually is much broader than that, and you can talk about the electrical properties, for instance, of biological systems like cells. And just to give you an example, I mean that's beyond the scope of the course, but just to show you, I just Googled for electronic properties of cell membranes, and there you could see this is a website called Scholarpedia. It's kind of like Wikipedia, but for scholarly type subjects, and you can see their electronic properties of membranes. And if you scroll down here um, to the subjects, you'll see here there's conductance, capacitance, and so on. Well, instead of conductance, you can think about resistance. So resistance and capacitance, that's exactly what we're going to be studying today. Now, in physics, we tend to study these things in a fairly abstract way. Okay, so I am going to be drawing, the kinds of diagrams that you would then go into a lab and actually hook up to build, the circuits like we have been doing in the virtual labs that we've been doing online. But these things apply perfectly well to biological systems and in a lot of different situations. So these are still quite general, okay? But it is emphasizing the electrical properties of things in matter. Okay, so that's why it's more like an electronics versus a more pure electricity. Okay, so let's start. So the first things we're going to study are voltage, currents, and resistance. Okay, so voltage you've already been introduced to last class, and you're going to hear me use the word voltage and potential quite synonymously. They mean the same thing. Okay, and don't forget potential is different than potential energy. Okay, so what is voltage? And just to remind you, voltage is defined as the amount of energy per unit charge. Okay, and so it's not how much energy there is, but for every unit of charge that's in your circuit, okay, you're going to have so much energy associated with it. And you can see that from the units. The units of voltage are volts. Okay, and a volt by definition is a joule per coulomb. Okay, so 1 volt basically says, look, for every coulomb, which is a lot of charge, okay, but for every coulomb I'm just going to deliver one joule of energy. By the way, a joule is kind of small. It's not a lot, all right? And a coulomb is kind of big. So a volt is really not that big, okay? When you've got like a 9-volt battery, that's pretty small. You can't do a heck of a lot with a 9-volt battery. Your wall socket delivers 120 volts. That's a little bit more, okay? So, but a volt is not a lot, okay? So it's kind of a small unit, all right? All right, so what kinds of things deliver voltage? And they could either be a power supply or a battery. The first battery was actually discovered by Alessandro Volta, and what he did was he just layered organic material actually, and different metals. I'm not even sure what, but he basically created a pile, which was like these alternating layers of things, and it created a potential across there, and he was able to, do electronics experiments with that. Okay, the symbol that we're going to use is this symbol right here. Okay, now I exaggerated it a little bit. I put a lot of long and short dashes in there. Usually there's at least two. There's at least one long and one short dash, but sometimes there's like four, two long dashes and two short dashes. The long dash part of it, that's the positive, and the short is the negative part of the battery. Okay, so there's your symbol for a battery, and when I draw electronics components. In a minute, you're going to see that, okay? Now, there's just one thing you need to notice about when I talk about current, which I'll do in a second. Current really is the flow of the electrons. It's actually pretty complicated. I don't want to get into, the quantum mechanics of band theory and that. But, if you just want to think naively, it's the electrons which do all the flowing. And the reason is because the electrons are kind of the fluffy things in matter. Okay, they're very light compared to the nuclei of the atoms. So the nuclei of the atoms, they pretty much stay in place, and they form the lattice of the structure of matter, and the electrons, they're the ones that float around. So electrons, they're actually generated at the negative side of the battery, and they'll flow to the positive side. But, we didn't know about electrons for maybe 100 years, until the Millikan oil drop experiment, okay, and Crookes tube, okay, those were the two major experiments that in which we discovered electrons. So we didn't know about that. And so unfortunately, today, conventionally, we always draw the current as flowing from the positive to the negative. Okay, but in reality, the current, it's the electrons flowing from negative to positive. Okay, just kind of a minor point. It's not that big a deal. But if you say, why are you drawing that arrow out of the positive side of the battery into the negative? I thought it was the electrons that flowed the other way. It is. It's just that, once you've adopted a kind of a convention, you stick with it. Okay, so there's a story with the positive and the negative in the current flow, but I didn't tell you what current was yet. So let me define for you the next concept that we're going to need, and that is current. Okay, so when we hook up this battery in a circuit, electrons are going to leave the negative and flow to the positive, and they're going to do that at a certain rate. Okay, it's like, it's probably going to be in the billions or 10 to the 12 electrons per second or something like that. But a whole bunch of electrons are going to leave the negative and they're going to travel to the positive. The rate at which they do that, that's called the current. Okay, and so basically, if you take a look at a particular point in the wire, now we'll see that in some of our circuits we'll have branching. Okay, and so the current can be different in different parts of the circuit. But if you're looking at a particular point in the circuit, all right, and you say, well, how much charge flows past this point per second? So here's the amount of charge, and here's the amount of time. So you just, you can't see them, but if you imagine you could, and you just had a stopwatch there, and you go tick, 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 10 electrons per second, that's a current. Okay, now we don't measure in electrons per second or number of electrons per second, but what we measure in is another unit. Okay, so the units here for current are actually amps, and the way that works is the units of current are equal to the units of charge divided by the units of time. And the units of charge is a Coulomb, which is pretty big. And the units of time is a second, which isn't that long. So if you have a Coulomb flow by a point in your circuit per second, that's an amp. Okay. Now, as you can imagine, an amp is pretty big. The reason an amp is big is because a Coulomb is big, and a second isn't that long. So if you get a whole Coulomb of charge flowing past the point per second, that's pretty big. Okay, so typical measurements of currents in a lab are down in the microamps or milliamps. Okay, they're not. It's not that much current. I got to say though that you can get a lot of current traveling through something. Remember, one isolated Coulomb of negative charge is a lot. Like if you had one Coulomb of electrons and no protons there, no positives, that's an awful lot of negatives in one spot in space. That's going to blow apart. Okay, there's just no way you're going to be able to hold together one Coulomb of negatives without positives. But most matter is both positives and negatives, so that it's charge neutral. Okay, so the way it works in a wire is, yeah, you get a lot of current, but as the negatives flow out of an area, negatives will flow in, so that any part of the wire stays charge neutral over time, but the input and the output of the electrons could be very big. Okay, so I hope that makes sense. It's kind of like water flowing through a tube. Never do you get water building up or water, kind of depleted where you get a vacuum in there or something like that. You're going to have a lot of electrons flowing in and a lot of electrons flowing out of that, so that it always stays charge neutral. You'll never have more electrons or less electrons than protons, but the amount of electrons flowing in and the amount of electrons flowing out can be pretty big. So you can get quite big currents, and in a house, you can get currents up to 15 to 20 amps, okay? Now, that's the point at which you're going to blow fuses. There are some demanding appliances like your refrigerator or your vacuum cleaner, and everyone's done this, where you've plugged in too many things into the wall socket on a particular circuit and it blows the fuse. We tend not to use fuses, we tend to use breaker switches, but it's the same idea. Once you start to get up to like 15 amps or 20 amps, depending on the size of your breaker switch, it's going to flip. Okay, it's going to turn off the circuit. And the reason it's going to do that is because of Joule heating, which we're going to talk about in a second. You don't want to start a fire with too much current. Okay, so just to recap here, current is the amount of current flowing through a particular point in space per second. Okay, so it's the coulombs per second flowing through a point, and that's given the name of an amp, named after a physicist that we'll study a little bit later, who played with magnetism, called Ampere. Okay, all right, so now we're actually ready to hook up a circuit. And here it is. Here's our first little simple circuit. What do we have in here? Here we have a battery. Okay, and the battery, and you notice I've got the arrow flowing out of the positive. I didn't put the plus there. Sometimes I do. The long part of the symbol of the battery, that's the long stroke, that's the positive, and usually you show current flowing out of that. So you can see here that arrow there, that indicates a current. There's so many, so much charge flowing out of the positive, and it's traveling through this resistor. And I haven't introduced a resistor yet. I will in just a second, okay? And then it flows back here and to there. Now you pick a particular point in space, like say that point right there, and you go, okay, how much charge is flowing through that point per second? There's your I. Now, because this circuit doesn't have any branches, whatever I is through that point there, it's actually the same I through all of it. If you had different currents at different points, like if the current up here were bigger than the current down there, that means that more is flowing into this resistor than is flowing out of it. Like, how's that possible? Would the electrons just build up in there? So you can't, if you had current, like not for a long period of time, if you had more current flowing in than flowing out, then charge would either build up or deplete, and so that's an impossibility. Okay, so the current throughout this whole circuit is the same, even though you might just say, you know what, I'm going to measure it right at that point. And I'm going to look in there and I'm going to watch how many little charged particles flow by per second, and I'm going to count them, and that's going to be convert that to coulombs per second, and that's going to be my current in amps, okay? Okay, now you don't actually look at them. What you do is you use a multimeter, and well, that's part of the lab, but basically you insert the multimeter right there at that point, and that'll tell you the current through that point there. Okay, now the next thing is this resistance. Okay, so the battery's kind of like the push. It's giving energy to each one of those charged particles to go out there and flow around there. If you didn't push them out, why would they move? Okay, so it's the push, and the current is how many of them are going to be flowing through, and the resistance is exactly that. It's kind of an attempt to slow down the current. Okay, now in an ideal world, where your wires just allowed as much electrons to flow as possible, as much current to travel through them as possible, and a battery which just had all the energy in the world, if you hook this up, then the current would go infinite. Okay, it's like you're pushing these electrons and there's nothing holding them back, so they're just going to flow. You're going to get these infinite currents. Okay, well that doesn't happen. That's not physical. Every wire in reality has some resistance to it, and so resistance, the easiest way to define it is it's some property of the circuit which basically limits the flow of your current. Okay, so because you're not going to get, for your battery, you're not going to get like an infinite amount of current flowing out of it. Well, that's because there's actually an internal resistance to the battery itself, but not more than that. The wire itself is simply just not going to be able to sustain certain currents, and so whatever limits the amount of current that you get per volt, that's called a resistance. Okay, and that gives you the clue to how resistance is defined. It's like the limiting of the current per volt. Okay, and so resistance is actually defined like this. Okay, so the resistance R is equal to volts divided by I. This is actually called Ohm's law. Okay, and let's see if we can understand it before I give you the units and we do some problems with this. Basically, the more voltage there is, the more push you have behind your electrons, the more electrons you're going to expect to flow through this, okay? And so as you increase your voltage, your current is going to increase. The ratio of the two is the resistance. If you've got very little resistance, then it doesn't take a lot of voltage to push a lot of current. So if very small resistance, V is small, R is small. I is big, R is small, okay? So you've got that kind of reciprocal relationship between R and I. Okay, the bigger I is, the smaller the resistance must be. Okay, conversely, the bigger the voltage is, the bigger the resistance is, or the smaller the voltage is, the smaller the resistance is. Okay, so there's Ohm's law. So once again, like it's resistance is like for so many volts, how much current do you get flowing through it? The more the more voltage you need to push that current through, the bigger R has to be. And the bigger I is that you get for a particular voltage, the smaller the resistance is, okay? Because a small resistance isn't doing a very good job at limiting your current, okay? So just think about that for a little bit. And so what are the units of ohms? Well, of resistance, sorry. The units are ohms, okay? And they're given this symbol omega, which is the last letter of the Greek alphabet, capitalized like that. And it's basically from Ohm's law here, 1 ohm is defined as a volt per amp, okay? Now, if you think about this for a second, an ohm is very small. Why is an ohm small? Well, a volt, we just finished arguing, is not a lot of it's not a lot of potential, okay? Remember, a volt, it's like for every Coulomb of flow, that's just 1 joule of energy. A Coulomb is big, a joule is small, so 1 volt is not a lot of potential. It's not a lot of voltage, okay? An amp is big, okay? That's like 1 Coulomb flowing past a point per second, all right? So volt is small, amp is big, so an ohm is pretty small, okay? Typical size resistors in the lab are kiloohms, all right? And you can measure the resistance of anything because, to the degree to which something limits current, it has a resistance, okay? So for instance, something that just absolutely doesn't allow any current to flow at all, that has infinite resistance, all right? Because, there's just no current at all. So this is a very good resistor. It's basically limiting all the current, all right? But, human tissue has a resistance, and I remember measuring my own resistance of my own body by just holding 2 leads of a multimeter together, okay, and finding that it's up in the hundreds of mega ohm range or something like that. Don't quote me because I don't remember that well, but you can get like into the mega ohms and so on, all right? But typical size resistors in a lab are in the kilo ohms range, all right? So there you go. I already said that. All right. One more thing before we can do problems, and this is actually heading towards Joule heating. What is it that resistors are doing to limit the flow of electrons? Okay, well, if you go back to the last video, and you think about this electron that was accelerating between 2 parallel plates, that's a very good model to have in your head. Basically, when you've got a potential drop between 2 areas of space, there's a electric field in there, and wherever there's an electric field, charged particles are going to accelerate, okay? And so what did that electron want to do in that electric field? It wanted to accelerate. In fact, it accelerated quite a bit. It didn't take very long. I think it was only like 7 centimeters, and it's already at 5% the speed of light. So that's quite an acceleration. That's like far beyond anything that's imaginable to us. We only experience like 10 meters per second squared, 9.8 meters per second squared. This is like orders and orders of magnitude higher than that, okay? But, that's in a vacuum. You could still have, 1,000 volts, but now across a wire, across a resistor. And those electrons, they're still experiencing that electric field, because it's the same voltage drop, maybe the same distance, so same electric field. But now it's an electric field in the context of matter. And so you wonder, what's happening to these electrons? They're not in a vacuum. These electrons, they're moving in matter. And so you can think of them as kind of like, the atoms as being these hard centers. And these electrons, here's an electron, this tiny little electron, the tip of my finger here. And it feels this electric field, and it gets accelerated. But it just can't travel that far before it hits an atom. And so it goes zoop, boink. And then, it hits it and it bounces off of it, okay? And then, now it's out here, and then it starts to accelerate again because it's being accelerated this way by the electric field. So it accelerates again, and boink, it hits another atom, boink, it hits another atom, boink, it hits. And so these electrons, they keep getting accelerated. They speed up, but then they smack into these atoms. And when they do, they're transferring their energy to the atoms, or molecules, depending on what the material is made of. And so these electrons, they're accelerating, but they don't have much. They don't accelerate for very long. They don't have much. They certainly don't have 7 centimeters of distance before they hit something. They hit something pretty quickly. Okay, like the distance between atoms is like somewhere like about zero point 0.1 nanometers. Okay, so they don't travel very far before they hit another atom. They hit another atom. They hit another atom. And as you can imagine, every time they hit an atom, what are they doing? They're transferring their energy to that atom. Okay, or molecule. Okay, they keep transferring the energy, and you can imagine all these atoms and molecules in the solid. They're starting to get energy. They're starting to get energy. They're starting to get energy. As soon as their energy builds up, well, you know that the average kinetic energy, we know this from our thermodynamics, the average kinetic energy of these atoms and molecules, that's the temperature. So what happens is in a resistor, as the electrons flow, they transfer their electrical energy over to the atoms and molecules of the solid. This means that they're moving faster and they heat up. This process is known as Joule heating. Okay, it can't happen in a vacuum because the electrons have nothing to hit. That electron in that parallel plate example, it just accelerated until it hit ultimately the plate. Okay, but in a solid, it doesn't have that chance. It's going to hit things pretty quickly, and so it's continuously transferring its energy. And actually, this is what's known as Joule heating. Okay, so this paragraph here is basically all to describe Joule heating. And Joule heating, you can actually work out as a power transfer. Okay, or power. Okay, now what is power? Power, we actually saw that when we were looking at the intensity of sound. We had watts per meter squared, but basically power is defined as how much energy is delivered per second. Okay, so it's not just like 10 joules of energy. It's like, because this is a process that's going on, it's like 10 joules of energy every second. Or a microwave oven. My microwave oven is actually rated at 900 watts. Okay, or that light bulbs are like 100-watt light bulbs. The old incandescent light bulbs, like 900-watt, 100-watt light bulbs, or 50-watt light bulbs, or things like that. Okay, so that 900 watts of my microwave oven, what that means is that microwave oven is actually delivering 900 joules of energy, but every second. So it does it over and over and over again. So 900 joules per second, 900 watts. Okay, so basically, power is just by definition. Those 3 lines there in math just means by definition. I don't know if I've mentioned that before, but I'm mentioning it now. So basically, power is just the amount of energy delivered per unit time. Okay, and the units of power is a watt. Okay, and we saw it earlier, but now it's time to define it a little bit better. And basically, a watt is 1 joule per second. Okay, now we can actually work out the Joule heating directly from our the theory that we developed last time, because there's a relationship between your potential and how much energy is delivered. Okay, so this delta U, okay, basically that's like your change in potential energy from, say, one plate to the other, or in the circuit from one point in the circuit to another point in the circuit. It's basically how much energy is delivered over by the current to the matter. Okay, to the atoms and molecules. So that's going to equal the charge multiplied by the voltage. Remember that from last class. So basically your potential energy is equal to QV. And so, if you have a potential difference in some point in the circuit, and there's a certain amount of charge that travels through that, then it's going to deliver over an energy delta U. Now, if you take delta U and you say, okay, well, that's how much energy is delivered, but how much energy is delivered per second? So you take delta U and you divide it by delta T, that's going to give you the power. But now if we substitute QV for your delta U, sorry. That happens every once in a while. Okay, so you basically substitute QV for delta U. So I called it here delta Q. It's like, because this is happening as a process, you've got basically your delta Q. That's how much charge is traveling through a segment of the circuit per second. Okay, but delta Q divided by delta T, that's your current. That's exactly what we mean by current. So basically, when you take the delta U and you replace it with QV, the Q, that's how much charge is flowing through there. But now you've got a per second on the bottom, so it's how much charge is flowing per second. That's your current, okay? And now, so you get that the power is basically equal to the current times the voltage, and ta-da, there you go. There's the formula for Joule heating. Okay, so basically, if you have a section of your circuit, say it has a resistor in there, and you know how much current is traveling through that resistor, and you know the potential drop across the resistor, the voltage across the two. Okay, you multiply the voltage times the current, there's your power. Okay, that tells you how many joules per second is being turned into heat there. Okay, and in one of the labs, we actually would have done this physically. Okay, and you would have actually touched this resistor and you would have seen that it got hot. But you know what? It's not that hard to imagine because Joule heating happens everywhere. If you have a light bulb, 100-watt light bulb, you don't want to touch it because it gets pretty hot. You go, where's that heat coming from? Well, guess where that heat's coming from? That's coming from the Joule heating. Okay, so you got so much current traveling through that tungsten filament, and you got so much voltage across that there because the tungsten filament has some resistance, so there's a voltage drop across the tungsten filament, and there's so much current going through there. You take the voltage, multiply it by the current. There's the power that is being dissipated as heat. Okay, so there you go. By the way, one of the reasons we've switched from the old style light bulbs with the tungsten filaments to the LEDs is that LEDs are just much more efficient. Like, a 15-watt LED is probably much brighter than a 100-watt light bulb. And the reason is that, yeah, you were getting some light out of that 100-watt light bulb, but most of the energy was being turned into heat. But you didn't buy the light bulb to produce heat. Maybe you did, like, I don't know, you want to heat something up with a light bulb. But, mostly we buy light bulbs for the light. And the light was just a little bit of the energy. And the heat was a big portion of the energy. And so you were wasting all this electrical energy as heat from Joule heating. And you were just getting a little bit of light. Whereas if you touch an LED in those LED light bulbs, you'll see they don't get very hot. So there, almost all the energy is becoming light, and very little of it is actually being lost to Joule heating. Okay, so that's why they're more efficient. All right, or another example of Joule heating is like an electric stove, where you have the elements on top, and those elements, they're basically just huge resistors, and you're putting a lot of current over those resistors. So you have a big I, and they have a lot of resistance, so they have a big V. Big V times a big I means a lot of power. So there's a lot of heat being released there. Okay, so lots of examples of this. All right, so there we go. There's Joule heating. Last thing is, depending on the problem that you're working with, you might want to combine the Joule heating formula, which is P is equal to IV, with Ohm's law, which is R is equal to V over I. Okay, and if you do, and I didn't even bother doing the algebra, it's pretty easy, but if you combine the two, you might see that the Joule heating can be written as I squared times R. Basically, what you did is you took the V and you eliminated V using Ohm's law. So you take this formula here, P is equal to IV, okay, and you eliminate V in terms of R and I using Ohm's law, and you get this form. Conversely, you can eliminate I. So here you eliminated V, here you eliminated I, okay, using Ohm's law, and it's the same. So it'll give you the same answers, just like it depends. Like, what did I give you in the problem? Did I give you current and resistance? Well, then you can use this one. Did I give you voltage and resistance? Well, then you can use that one. But you know what? If I give you voltage and resistance, then you can calculate I, and then you've got voltage and I, and you can use the previous one. So it's just a minor thing. I just wanted to mention it in passing because, if you look at the labs or if you look at other places online, you might see the Joule heating being written this way, and you're going, well, that's not the way I taught it, but it is. It's the same. It's just basically the Joule heating formula, P is equal to IV, combined with Ohm's law. All right, now we're ready for a couple of problems. Okay, so how much current does a 100-watt light bulb draw? Okay, and what is its resistance? And note that the voltage in our houses is 120 volts. Okay, so I'm going to give you a little bit of a caveat here. I don't want to get into in this course the difference between DC voltage and AC. Technically speaking, what I did here is not exactly correct because it assumes DC voltage, which is direct current. It means a constant potential of 120 volts, whereas our electricity in our house is actually alternating. Okay, I just wanted to mention that because I didn't want to mislead you. Okay, but nonetheless, let's assume that our houses were actually powered with 120 volts DC direct current. That is, the voltage doesn't change over time. Okay, well, we have that the power is 100 watts. Okay, and we have the voltage is 120 volts. And so I gave you the power, I gave you the voltage, and I asked you for the resistance. okay, and current, but we could do whichever one you want first. And so over here, you got the power is equal to V squared over R. So you can rearrange, you could say R is equal to V squared over P. And if you plug in there, you find that your light bulb has 144 ohms resistance. It's actually very small. It's a very small resistance, okay, which allows for a lot of current to travel through it. Small resistor doesn't limit the current much, so you're going to get a lot of current traveling through it. And so now that you have the resistance, you can go ahead and use Ohm's law to get the current. So V is equal to IR, or you can rearrange that I is equal to V over R. So V is 120 volts. The resistance is only 144 ohms, and so you get 0.833 amps, okay? And so you can see that 100-watt light bulb is actually going to draw 0.833 amps, okay? So it doesn't take a lot of them before you're going to add up to about 15 amps, and then you'll throw your breaker or you'll blow your fuse, okay? All right, there's one example. Now, this next example is not exactly an Ohm's law, but I did want to give it to you because, when you get your electrical bill, one day when you have to pay electricity, you own your own home, you're going to have to pay your own electricity, or have an apartment where you have to pay your electricity. You're going to look at your electrical bill and you're going to say, well, is this right? How did they calculate it? So I just wanted to give you the unit by which electrical power is actually, or electrical energy is actually sold to you. It's a very funny unit. It's called a kilowatt hour. And so I asked how many joules of energy is in 1 kilowatt hour. And that's how it's written. 1 kW, there's your kilowatt an hour, okay? And so electricity is sold in these kilowatt hours, and it's pronounced kilowatt hours. You say, well, how many joules is that? I don't know what a kilowatt hour is. It's actually a measure of energy, not power. It's a measure of energy, okay? And so it's like, how much energy did the electric company give you in the last month? And so 1 kilowatt, well, that's just 1,000 watts. And I'm going to write the watt as joules per second here, like that. So 1,000 joules per second. And an hour is 3,600 seconds. You'll notice that the seconds cancel out. And if you multiply this all out, you're going to get 3.6 megajoules. Okay, so that's a lot of energy. That's a kilowatt hour. And I looked up before the class. I just said, you know what, what are electrical rates? And it turns out that a kilowatt hour is only 13.9 cents on average, okay? So that's an awful lot of energy for very little money. It's a pretty good deal, okay? Natural gas is even cheaper for the same amount of energy. But there you go, okay? So energy is, you might think that electric bill is pretty expensive, but energy is pretty darn cheap, okay? All right, so let's go back to our notes here. And let's move on to our next topic. The next topic is resistors in series and parallel, okay? So once again, I want to remind you that, like we're doing this theory in the abstract, but, this could be applied to lots of different situations, like even biology, all right? And so, you can have situations where you have like cell membranes, and cell membranes have a certain amount of resistance, and you might have membrane after membrane after membrane after membrane, okay? And, you have a resistance for the first layer, and then a resistance for the second layer, and a resistance through the third layer, and so on. And whatever the current is, has to maybe travel through all of them. And so you want to say, well, what's the effective resistance of this particular situation? And so that's where resistors parallel and series comes into play. Okay, so again, the theory is abstract here, but it can apply to lots of different situations. And so let's go through it. Okay, so here we have a circuit, and it's basically your battery. Okay, and instead of just hooking up one resistor, I've got two. Okay, and they're in series. And what series means is that there's one right after the other. So the current is forced to go through both of them. That's really the definition of series. So the same current, I didn't draw it in this diagram, but like I drew it above, it's the same current. The current that goes through here, it doesn't split, okay? So whatever the current is, let's say it's 1 amp. That 1 amp of current is forced to go through R1, and then it is forced to go through R2. The same current is forced to go through both resistors, one after the other. That's what series is. It turns out that two resistors in series is totally equivalent to just one resistor of a particular value, okay? And so there's a relationship between R1 and R2 and their equivalent resistance, all right? So two resistors in series act like one resistor in series of a particular value, which you can calculate from R1 and R2. If we were building a circuit, you could literally pull out R1 and R2 and replace them with R equivalent, and all the other electronic properties should remain the same, like the current and the potential, okay? So how does that work? Well, it turns out, and I'm actually going to prove this, it turns out that the equivalent resistance is basically just the sum of the two resistances, which you might have imagined because, you're a current and then first you hit R1 and then in addition to that, you have to hit R2. So you're feeling twice, not twice as much, but you're feeling the sum of the resistances. Okay, you're not able to avoid R1, you're not able to avoid R2, so the accumulated resistance is the sum of the two, intuitively speaking. But it is useful to prove this. Okay, so I'm going to prove it because it's actually going to, the proof that I have here is actually going to be something that we're going to use when we analyze more complicated circuits in a minute. Okay, so the first point you have to realize in proving this, that R equivalent is equal to R1 plus R2, the first thing is that energy is like voltage. Energy basically adds. Okay, now what that means is that there's a certain voltage here. Okay, so there's a certain voltage here, and there's a voltage drop across the first resistor, and then there's a voltage drop across the second resistor, and the sum of these two voltage drops, we can call them V1 and V2, must add up to the total V. Okay, if this were energy, and think about energy being turned into heat, suppose that the first resistor, I'm just making up these numbers, but suppose the first resistor dissipates 1 joule of energy per second, and the second resistor dissipates 2 joules of energy per second. Well, the first one is making 1 joule of energy into heat per second. The second one is making 2 joules of energy into heat. Together, they're making 3. Okay, so basically, just like energies add up, voltages will also add up. Okay, so with that in mind, we can write the following equation. Okay, so I didn't draw the whole circuit, and you're going to see me doing this a lot. I'm just drawing the two resistors. All right, but the understanding is that the voltage drop across both of them together, like if you were to take a multimeter and put it into voltage, so that you're measuring voltage, it's called a voltmeter too, but it's usually done with a device called a multimeter, which allows you to measure multiple different electronic properties, and you put one of the probes over here, okay, and you put the second probe across both resistors, and you measure the voltage across both of them, that's going to equal the voltage of the battery. Okay, so that's what I called V here. That's your total voltage drop. Well, now you could take that same multimeter and just measure the voltage drop across just one resistor. That's what I called V1. And you could take the multimeter and measure the voltage drop across R2, and that's V2. And what you would discover, if you did a careful measurement, is that V, the total voltage, is just going to be V1 plus V2. Okay, so I'm just restating what I did earlier intuitively. You would actually see this in the lab. Okay, now the next thing is, we've got voltages there and we've got resistances, and we want to actually get the effective resistance. The way you can think about this is just apply Ohm's law. I scroll down a bit too far. Okay, okay. Good enough. So Ohm's law can be applied to the whole circuit, but it also can be applied to segments of the circuit at the same time. And the other thing to keep in mind is that the current through both of those resistors are the same. In fact, that almost defines what you mean by series. The same current that's flowing into R1 has to also be flowing into R2. Okay, it can't be different. If more flows into R1 than flows into R2, well then where's this extra charge going? Remember, current is just charge per unit second. So if 10 electrons flow into R1, but only 5 flow into R2, there's like 5 extra per second. What are they building up? 5, and then next second 10, then 15, 20. They'll just keep building up. So since the charge can't build up, or electrons don't just appear out of nowhere, okay, whatever flows into R1 has to also flow into R2. Or whatever flows through R1, probably a better way to say it is whatever flows through R1 will also have to flow through R2. Otherwise, you have a buildup. Okay, all right, so you can apply Ohm's law to the two resistors independently of one another or together, and keep in mind that the current is the same. So if you apply it to the whole circuit over here, you're just going to get that the total voltage drop across both of them is going to equal the current, which is the same throughout this problem, multiplied by the effective resistance. Okay, that's just Ohm's law applied to the whole circuit. All right, but if you apply Ohm's law just to R1, then that's going to say that the voltage drop across R1 is just V1 is going to equal the current, which is the same for all of them, multiplied by R1. And the same thing for R2. The voltage drop across R2 is V2, and that's just going to equal the current through R2 times R2. Okay, so there we go. We've got these three equations All right, and now we can take them. Notice this is V, V1 and V2. And we can plug them into equation number 1 here. And when we do, and we eliminate V, we basically this was our total V, but now we're going to write I R equivalent, and this is our V1, and now we're going to write I R1, and there's our I R2 for V2. And notice that the I's cancel out because they're the same for all of them, and ta-da! You get that the equivalent resistance is basically the sum of the two resistances in series. All right, so there you go. That was the proof. Now, keep this in mind because this idea of applying Ohm's law both locally to different segments of the circuit and also applying it globally, we're going to use that quite a bit in our problem below. And students sometimes get confused when these problems get too complicated. So I'm going to try to go through that slowly, and you'll see that at every point you're going to go, oh, I know V and R, so I should be able to find I. Or conversely, you might know I and R, and you should be able to find V. Okay, and by going back and forth this way, you'll be able to solve these problems. Okay, so it's the same technique. That's why I did this proof. It's the same technique in proving this that's also used in solving some of these problems, which we'll see in just a second. All right, now there's series. Here's parallel. Okay. So what's happening here? Parallel means these two resistors are side by side. The situation's kind of different now. Here I drew the current because something very interesting happens here. So here's a current, but it gets to this point right here, which is a junction, and the current splits. It splits into I1, which goes through R1, and I2, which goes through R2. Why does the current split? Well, let's think about it. Remember what current is. It's charge per unit second. So let's think in terms of electrons. Suppose 10 electrons are coming in here, and 3 electrons go through R1. Well, then 7 have to go through R2. Okay, why? Well, because the number of electrons is conserved. If you've got 10 coming in, 3 are going one way, 7 have to go the other way. Conversely, if 4 go one way, 6 have to go the other way. Okay, the sum of the current going in has to equal the sum of the current coming out of that junction there. All right, this is a different situation. All right, now let's write that down. There's our equation. The current, the total current, basically gets split between I1 and I2. All right, and such that because matter is conserved, okay, such that the two branches have to equal whatever's feeding them. Okay, so I is equal to I1 plus I2. Now we once again apply Ohm's law, but this time we want to eliminate the I's. Okay, now the total I is going to be equal to the voltage across the whole circuit divided by the equivalent resistance of the whole circuit. Pick one resistor, R1. The current through R1, let me just show you the diagram again. I1 is going through R1 and I2 is going through R2, okay? The current through R1 is V divided by R1, and the current through I2 is V divided by R2. Notice it's the same voltage for all of them. You go, well, why is that? Why doesn't the voltage split? It doesn't. Voltage, in fact, we even say it voltage drop. You have to think of it as like if you're at a certain voltage, you have to pass through a component before you go to a different voltage. Wires do not change your voltage. So let's just pick a number, 10 volts. Suppose up here you're at 10 volts. Okay, so this is the 10 volt side of the battery. This is 10 volts, 10 volts, 10 volts, 10 volts, 10 volts. You get to that junction. It's not like a current. It's an energy. It's like, that analogy I gave you in the last video is you're so high above the ground, okay? Making the analogy with gravity. So you're at 10 volts height. You're at 10 volts height. You're at 10 volts height all the way through here. You're at 10 volts height all the way through here. So both of these resistors start off at 10 volts. And what do they get down to? Well, this other one is at, say, 0 volts. So the bottom of the resistors, both of them are at 0 volts. Well, the top of both resistors is at 10 volts, and the bottom of both resistors is 0 volts. So the voltage drop across both resistors is 10 volts. It's the same. The voltage drop across both of these are the same. Okay? So when you have things in parallel, unlike the series where the voltage is at, in parallel, the voltages are the same across the two. It takes a little bit of thinking, but you'll get it. Okay? So let me just go through it again. The current splits here, but the voltages are the same. Whereas in series, the voltages split, but the current is the same. So it's kind of the opposite. All right. So now That explains why this V is the same for all of them. Okay, so we have the total current is equal to the total potential divided by the equivalent resistance. But for resistor number one, I1 is equal to V over R1. That's Ohm's law applied just to that one. And for resistor 2, applying Ohm's law to just that one is I2 is equal to V over R2. Now we have this equation here, number 2. Let's plug in for the I's there. And we've eliminated the I's. Now we have them in terms of V. The V's are all the same. They divide out and ta-da! You get the formula for the effective resistance when the resistors are in parallel. This is kind of interesting. It's not the resistances that add, it's the reciprocals that add. And so basically you do 1 over R1 plus 1 over R2. That doesn't give you R equivalent, that gives you 1 over R equivalent. Okay, and so make sure you know how to do this on your calculator. And I can't really show you how to do that on a calculator online very easily. Maybe during one of the Google Hangouts or something I can try to show you that. But basically you would do 1 over R, whatever the R1 value, plus 1 over the R2 value, and you would get a number. And then you would take the reciprocal of that number, that total, and that would give you the R equivalent. Okay, and that's what you do for resistors that are in parallel. Okay, actually, what I did above is I kind of snuck something in known as Kirchhoff's laws. Now, we're not going to study Kirchhoff's laws formally, but they can be used to analyze very complicated circuits. And since we already kind of implicitly use them, I might as well mention them. But basically, Kirchhoff's laws, there's 2 of them. One of them says that if you take any circuit and you go in a loop, and you add up all the potential drops and all the potential gains, they basically have to add up to 0 in any loop. Okay, and that's like saying, look, if you start a hike at a certain point, so we're doing now the analogy to gravity. If you start a hike and you're up at the top of a hill, if you walk down the hill and then you walk around and then you walk back up the hill, the amount that you walk down has to equal the amount that you walked up. How could it be that you wind up at the same point and the amount that you walked downhill is not equal to the amount that you walked uphill? Something would be very weird in that kind of a universe. Okay, and it's the same thing with voltage. The amount of voltage drops that you have has to equal the amount of voltage gains if you go in a loop. Okay, now a voltage drop occurs across a resistor, and a voltage gain, where does that happen? That's your battery. It basically says, if you go back to the diagram here, and this diagram has at least 2 loops. Here's one loop through R1 and then back to the battery. The battery gives you, let's say 10 volts, okay, for a number. The battery gives you a gain of 10 volts, and then the resistor gives you a drop of 10 volts. So that, the gain of 10 is going to be countered with a drop of 10. Okay, that's in just this loop here. If you did another loop, like through R2, avoiding R1 altogether, the battery gives you 10 up, and the resistor gives you 10 down. Okay, so that's just Kirchhoff's law. And I mentioned it in passing because it's kind of intuitive. It should help you to understand what's going on in these circuits here. Okay, and the other one is basically if you come to a junction in a wire, that's where the wire splits. Okay, well then the sum of the currents going into that junction has to equal the sum of the currents going out of that junction. Okay, and so basically that makes sense because electrons don't just appear out of nowhere and they don't just disappear. Okay, so in order to have conservation of the number of electrons flowing, you have to have this law. So what Kirchhoff's laws, 2 laws are. This is the first one is like conservation of energy, and the second one is like conservation of matter. It's a lot like the hydrodynamics that we did earlier, where you had the continuity equation and the Bernoulli equation. Okay, anyhow, so there you go. And now we're ready for our first problem. Okay, now this is there's a lot of steps to this problem. They're not hard, and I wanted to give you a lot of steps because I want to show you how by thinking this through, you can just keep applying Ohm's law over and over and over again locally, and you're able to solve the problem. Okay, so this problem asks for quite a few things. So let's keep in mind. First, I want the effective resistance of the entire circuit. Okay, and I've actually got 4 resistors in there hooked up in a kind of a not a very complicated way, but complicated enough. Okay, so I've got 4 resistors, and I want the effective resistance of the whole circuit. So combine all those 4 into one. Okay, and then I also want to know what's the current through each of the individual resistors, and also what's the potential drop across all of them. Okay, now getting the effective resistance, there's a series of steps in that. And then getting the current through each of them and the potential across each of them is the same steps, but backwards. It's like we fold it all up and then we unfold it, and that should answer this problem. So once again, we want the effective resistance of the whole circuit, and then by working the problem backwards from our solution, find the current through each resistor and the potential drop across each resistor. Okay, let's start. So here's the circuit. So this is a different way to draw a circuit. You say, well, I don't see the battery. I know. Sometimes circuits get a little bit complicated, and so rather than drawing a whole bunch of things, basically you could imagine that there was a battery attached like across here like that, and this battery is applying 10 volts here, and there's your 0. So this is like the positive side of the battery at 10 volts, and here's the negative at 0 volts or ground. Okay, 0 volts is sometimes called ground. Okay. All right, so the battery's not there, but if you were to attach it, you would attach it there to there, then you'd have the battery in here, and then attach it to there. So just because like outside of this course, you might see these diagrams again. You might see them drawn this way. So I'm showing you another variation on how they might be drawn. All right, now what do we have here? We have 4 resistors. This is a 10 ohm. There's a 7. Here's a 5 and a 3. Okay, and you ask, are they in series and parallel? And the answer is both. They're kind of mixed. And so you say, well, how do I reduce this? How do I get it down so that I would, if I were doing this in the lab, I would remove these 4 resistors and replace them with one effective resistance? And the answer is you have to do them 2 at a time, okay? Because if you look at the formulas above, they're just 2 at a time, okay? Now, you can relax that a little bit. If you've got 3 in series that are definitely in series, you could do it. But 3 in series is just 2 in series followed by another 2 in series, okay? So if you just reduce them 2 at a time, it'll still work. And that's the safest way to do it. So you take a look at the circuit and you say, are there any that are purely in either series or parallel? And you say, well, is R1 and R2, are they in parallel? Not quite, because there's these guys in the middle. Okay, so those guys are kind of messing it up. And you can say, well, is R2 and R3, are they in series? And no, because there's a split in there, and that's kind of messing them up. You have to kind of draw, like imagine drawing an imaginary circle around 2 of them and focusing only on those 2 and go, oh, those 2 are purely in parallel, or those 2 are purely in series. And there's only one pair that really you can start with, and that's R3 and R4. R3 and R4 are purely in parallel, okay? So if you try to combine, say, R2 and R1 first by saying, oh, they're in parallel, and no, they're not, because R3 and R4 are kind of like in the way, all right? And so, that imaginary circle would encircle both R3 and R4 like that, and if you just highlight those and you ignore anything else, they're purely in parallel, so start there, okay? Now, R3 and R4, oh, what did I do here? I wrote R4, R5. Sorry, that's R3 and so R3 and R4. I did it right below it, but over here I've got 4 and 5. That's incorrect. Okay, so R3 and R4, they're in parallel, and then you say to yourself, how do you add those in parallel? And the answer is, in parallel, you add the reciprocal. So here they are. Okay. Now the way I'm going to do the equivalent resistance for 3 and 4 is I'm going to call it R34. So R34 means the equivalent resistance for R3 and R4. Okay, I think that notation kind of makes sense. And I didn't even show you the algebra or the arithmetic. It's kind of boring. But basically, for R3, what was the value there? For R3, I put in 5, and for R4, I put in 3 ohms. So 1 over 5 plus 1 over 3. And then you work that out, and then you take the reciprocal of that, and you find that the effective resistance of 3,4 is 1.875 ohms. Okay, 1.875 ohms. So you could remove R3, R4 and replace it with one resistor whose resistance is 1.875 ohms. And so in the next diagram, there it is. Our circuit reduced from 4 resistors to 3 resistors, where R3 and R4 have been replaced with R34, which is equal to 1.875. Great. We're not quite there yet because we got to reduce it to just 1, but we're getting closer because we went from 4 resistors now to 3 resistors. Okay, great. Now what? Well, you play the same trick again. You just keep playing the same trick until you're finally down to 1. And you take a look at this, and once again, R2 is not purely in parallel with R1. Neither is R34 in parallel with it. If you draw a circle, it would just be between R2 and R34, R2 and R34. Those two together are purely in series, okay? So only R2 and R34 are in series, and so what do they do in series? They add. And so now my effective resistance I'm going to call R234 because it's the effective resistance of 2 and 3 and 4 all together. And R234 is R2 plus R34. And if I just add those up, I get 8.875 ohms. Okay. And so now I could take out 2, 3, and 4 and replace it with R234. And our circuit looks like this. All right. We're getting closer. And now there's only 2 resistors, and so you've only got 2 choices. They can either be in series and parallel. They're in parallel. In parallel, the reciprocals add, so you use this formula here. And again, skipping some of the boring algebra, you find that the effective resistance of the whole circuit, that is of resistors 1, 2, 3, and 4 all together, is 4.7 ohms. 4.7 ohms. Great. Okay. Now, I didn't draw that circuit, but there it is. Okay. Oh, I'm sorry. I guess I did draw that circuit. There it is. Okay. So it's all been reduced to just one. Now, at this point, you've answered part of the question. You've gotten the effective resistance of the entire circuit. Now we want to actually work out the potential drops and the currents through all of them. And to do that, you're going to have to start working backwards. And the way you do that is you think to yourself, what do I know right now and what am I trying to get? Okay. And you do that at every step as you work backwards, and you'll see what I mean by working backwards. Okay. And you'll be able to eventually find all of the quantities that I'm asking for. So right here, you have the total potential drop. So you have V, and you have the total resistance, which is R. And you're going, what's the other electronic quantity that I can get? I have V and R, obviously I, the current. Okay. And so the first thing you do is you get the current through the whole circuit. And the current through the whole circuit is, these are all Ohm's law. It's like literally applying Ohm's law locally and globally over and over and over again. So you just use Ohm's law applied globally. V is equal to IR. That's the way I usually have it memorized. I know above I gave you R is equal to V over I, but in my mind, I usually think V is equal to IR. And so what do we want to solve? Well, we know V and R is we want to solve for I, so we have I there. V, this is V for the whole circuit, is 10 volts. R, this is R for the whole circuit. I even could have written R 1, 2, 3, 4 there, okay? But it's basically the full equivalent R, and that's 4.70 ohms, and that turns out to be 2.128 amps, okay? So the circuit basically will draw 2.12 amps. That's the total amount of current that's being drawn into these resistors, all right? And so now you've got part of the way there, all right? What's the next thing? Well, we go back one step. We don't go back all of the steps at once. That's too much. You just go back one step. What I mean by one step is like before we had the circuit at this point, we had the circuit at that point, which was 2 resistors. So go from here, where now we know all 3 things, V, R, and I, because we just calculated that, and go back to this. All right, so what does that look like? That looks like this, and notice what I did is I also put in the currents there. So we have the total voltage drop is 10 volts. We have the current, the total current, which we know is now 2.128 amps. Okay, that current's flowing in through here, and ta-da, it gets to that first junction. So what happens at a junction? The current splits. Okay, so what's this current splitting into? I called this one I1. I1 is the current through R1, and I234 is the current through R234. Okay, and so that's the total current. I234 is the total current that is passing through resistors 2, 3, and 4 collectively. All right. Now, I don't know what I1 is, and I don't know what I234 is, but I know that the sum of the two has to equal 2.128. Okay, so that's basically my equation number 1 there. Why? Well, because, like we've said numerous times now, the current just can't appear or disappear out of nowhere. So if it's splitting, whatever goes in has to equal what's coming out. So what's going in? 2.128 amps are going in, and that's being split between I1 and I234. Great. We're actually not even going to use this equation. You could, but we're going to use it as a check. You'll see how that works out later, okay? By the way, when those two currents come together, when I1 joins up with I234, guess what? On the other side, they have to join up and they have to add up to the original again, which is 2.128 amps. Okay, great. Now what? Well, what do we have here? We have the resistances, 10 ohms for R1 and 8.875 for R234. What else do we have? We have the voltage drops across them. They're in parallel. And remember, in parallel, the current split, but the voltages don't. So the voltage drop across the 10 ohm is 10 volts. And the voltage drop across 234 is 10 volts. So this is 10 volts, 10 volts, 10 volts, 10 volts, 10 volts to there. And this is 10 volts, 10 volts, 10 volts, 10 volts to there. Okay. Then over here it's 0 volts, 0 volts, 0 volts, 0, and 0 volts, 0. So on the one side it's 10 volts and the other side it's 0 volts for both of them. So it's a 10 volt drop. I don't know how much you like analogies. I don't know if this helps or not, but you could think of this as like, being high up. It's like a 10 volts high. And this is like a little waterfall. Okay, and this has to drop. And then over here, this is all at 0. So this is like all at ground level. The analogy is there because we even say 0 volts. We call that ground. You've often heard, the electrical ground. Okay, that kind of means like, ground level. All right, and so this is all ground level. And over here on this other side, this is all at 10 volts high. And so if you go from 10 volts to 0, you're dropping 10 volts. So the drop across both of them is 10 volts. Again, I don't know if these analogies help, but the statement is true that the voltage drop across both of them is the same. Okay, so then you say, okay, well, let me just do this for R1. So for R1, I have V1 is equal to I1 R1. Okay, so we know that V1 is the 10 volts. That's the drop across R1 is 10 volts because it's the same for both of them. R1, it's 10 ohms, and guess what? Ta-da! We find that the current through R1 has to be 1 amp. Okay, so 10 volts is equal to I1 times 10 ohms. Divide 10 on both sides, you get 1 amp. All right, great. That gives you the current through I1. So the current through I1 here is 10 amps. You can already work, 1 amp. You can already work out what the current is through there using equation 1, but let's see that it's all consistent. All right, so you do the same thing now for the voltage drop across 234. Well, the voltage drop across 234, we just said, has to also be 10 volts, so there it is. And the resistance of the combined 234 is 8.875 ohms, and we find that the current through 234 is 1.127. Okay, and so we have 1 amp and 1.127. If you add them together, you get 2.127, and that checks out with equation 1. Well, not quite. It's off by, that would be 7 instead of 8, but it's just a round off here. Okay, so basically the current through R1 is 1 amp. The current through combined 234 is 1.127 amps. Together, the two have to be 2.127 amps, and that agrees with what we expected because the current into the junction has to equal the current out of the junction. Okay, so basically equation 1 there is just for a check, but it's a good check. Okay, and well, there you go. Okay, so now what do we know? Well, now we actually step back. We go back another step, and we make use of what we know there. And so going back another step, we had R234. We break that one up. And what does that break up into? That breaks up into R2 and R34. Now let's take a look at the currents. You'll see I have the currents there, and I've written in their values. So you've got a current coming in here. We know that that current is 2.128 amps. It splits into 1 amp going up this way and 1.27 amps going that way. I know that that's a 7 and that's an 8, but just a round off here, okay? So we've got the 1 amp going through the 10 ohm resistor, R1, and we've got 1.127 amps going through both R2 and R34. Why? Why is the current the same through both of these resistors? Because they're in series. So remember, almost the defining feature of series is that the current through both of the resistors is the same. So the current through R2 and the current through 3.4 is 1.27 amps. Okay. Now, over here, we actually know everything about R1. We know its resistance, 10 ohms. We know that the current through it is 1 amp. And we know that the voltage drop across it is 10 volts. So there's nothing more to do with R1. It's R2 and R34 that we have yet to further analyze. So let's take a look here. What do we know about R2? Well, we know its resistance. We know the current through it. And the same thing for R34. We know its resistance and we know the current through it. What don't we know? The voltage. So we can now calculate the voltage drop across R2 and the voltage drop across R3. We do know that the voltage drop across both of them has to be 10 volts because you're at 10 volts here and you're at 0 volts there. So if you jump both of them, it has to be 10 volts. So basically, you've got a little check. And the little check is that the voltage drop across 2, 3, 4 has to be whatever the voltage drop is again across 2 plus whatever the voltage drop is across 3, 4. Okay, and that basically means that 10 volts has to equal V2 plus V34. Okay, and there's my equation too. Again, we don't even need that equation, but it's just a really good check. It's a really good check to make sure that everything is working out consistently. And what do? You apply Ohm's law to both of them to find the unknown. In this case, the unknown is voltage. Previously, it was the current that was unknown. Okay, but that's because they were in parallel. But now they're in series, and so it's the voltages that are unknown. And so the voltage across R2 is just going to be equal R2 times I234. Okay, I don't know why I switched the order here. I mean, you could do IR or RI. I mean, I don't know, whatever. It's the same thing. But basically, the voltage drop across just R2 is going to be the current through R2 multiplied by R2. And you say, well, why didn't I just write I2? Because the current through the current through R2 is the current through 234. Okay, it's because they're in series, so it's going to be the same. And so, R2 is 7 ohms. That current is 1.127 amps. And so you multiply them together and you get 7.89 volts. Okay, so the voltage drop across just R2 there, okay, that voltage drop there is 7.89. All right. And now what do? You do the same thing for the other resistor, which is the combined 3-4 resistor. And so you get the voltage drop across 3-4 is R34 times I234. Okay, and the current through both of them is the same, so that didn't change, 1.127 amps. But the resistance, the combined resistance of 3-4 is 1.875 ohms, giving you 2.11 volts. Okay, now because the voltage drop across both of them has to be 10 volts, you can check. If I add 7.89 volts plus 2.11 volts, do you get 10? It does, so it works out. Okay, everything's consistent. Great, we're almost done. The last thing we need to do is, when we step back one more, is we break apart R34 into R3 and R4. Now, the circuit's getting kind of complicated, so rather than redrawing the whole circuit, let's just concentrate on R34. What do we know about R34? We know that the current through R34 is 1.127. We know that the effective resistance is 1.875, but we also know that the voltage drop across both of those is going to be 2.11 volts, and so we just draw that piece. All right, there you go. So what I drew, and I didn't even draw the current there because it's not that important, but the voltage drop across R34, we just calculated that. That's 2.11 volts. Okay, so this is just part of the circuit. It's not the whole circuit. It's just that R34 being taken apart into R3 and R4. Okay, so once again, the current is, this is in parallel. Whoops, went too far. This is in parallel. So the current that's going into that junction is being split. We know the current that's going in, that's I234. That was the 1.127 amps. That's going to split into I3, which is through the R3, and I4, which is through R4. Okay, and there it is. This equation, again, we don't really need it. It's just going to be our check to make sure that the current through both of those two resistors has to equal the total current into them. Okay, and we apply Ohm's law, and you just say, well, what don't I know? Well, you know the resistances, you know the current, you know the voltage drop. Sorry, I apologize. You know the resistance, you know the voltage drop across both of them, but you don't know the individual currents through each one of them, so that's what you calculate. So you use Ohm's law, which is V is equal to IR, okay, but apply it to number 3, to resistance 3. So V3 is equal to I3 times R3. Rearrange this because we're looking for the current through resistance 3. So I3 is going to be equal to V3 over R3. The voltage across R3 is 2.11. The resistance is 5 ohms, divide the 2, and you get 0.422 amps. So the current through R3 is 0.422 amps. You do the same thing for R4. so that I4 is equal to V4 over R4, and that gives you a current through R4 of 0.703 amps. And now you say, well, if I add these two together, are they going to add up to that 1.127 amps? They do. They do. Okay. Well, there's a round off here. Okay. If you do it, you'll see there's a round off here. It actually turns out to be 1.125, but I kept one extra digit just in case. Okay. So, that's in the third decimal place. It's just a small round off here. If you had done it better, this would have worked out perfectly. Okay. All right, great. So at this point, I didn't redraw the circuit, but you can go back and you can see that we answered all the questions. Okay, so I gave you the effective resistance above. I didn't repeat that here. That's that 4.70 ohms. That was, that was kind of like the halfway mark. Okay, and then when we work backwards, we found both the voltage and the currents across all the resistors. Okay, so for the 10 ohm, we found that one right away. The voltage drop across it was 10 volts, and it had a current of 1 amp. Okay, the voltage drop across R2, that was the 7 ohm, that turned out to be 7.89 volts, and the current through I2 was the same as the current through I2, 3, and 4, okay, because they're in series, and that turned out to be that 1.127 amps. Okay, R3, that was in parallel with R4, so it split that 1.127 amps into two. The voltage drop across R3 was 2.11 volts. It's the same as the voltage drop across R4, it was 2.11 volts because they're in parallel, but the current got split. Okay, so currents will split through parallel resistors, and that got split into the 0.422 amps and the 0.703 amps. Okay, and so it's a long problem, all right, but that's because I gave you 4 resistors. But with 3 resistors, this should be doable on like a test. Okay, you wouldn't have quite as many steps. You'd only have to go back twice. Okay, and work things out. All right, so there you go. There's the story of resistors. All right. So let's continue. We've studied certain electronic properties now. These are properties that are in circuits. And remember, circuits are not just things that you play with in a lab. They could be biological systems as well, okay, or any kind of a system where you have electricity flowing. And so the component or the properties we've looked at are potential. Okay, that's energy per unit charge. Okay, that's kind of like the push behind the electrical current. The current is the flow. That's how much charge is flowing per time. The resistance is what limits that flow. And now we have another concept, another electronic property, and that's capacitance. Okay. Now, what happens when current flows is I told you a minute ago that whatever flows into a component has to also flow out of the component, otherwise charge is building up. Can charge build up? Yes, only temporarily though. It can't go on forever. If charge kept building up forever, well then you'd have like some kind of an explosion because the matter, underlying matter, simply would not maintain its integrity with that much electrical force trying to pull it apart. If there's too many negatives in something and all the negatives want to get away from one another, eventually the negatives wanting to get away from one another is bigger than the other electrostatic forces at the atomic level trying to hold it together, and it blows apart. Okay, in some sense, that is what a chemical explosion is. It's exactly something like that. Okay, with heat in there and so on. But I don't want to get into the details, but you got an idea. Okay, but like you can have devices which will build up a little bit of charge. Okay, they can't go on to infinity, but they can build up a little bit of charge. And so basically, a capacitor is a device which acquires charge when a voltage is applied. Okay, so if you apply a voltage to a capacitor, it's going to acquire a charge. The more voltage you apply, the more push you put behind the charges, the more you're going to be able to push onto the capacitor, and the more charge will accumulate. Okay, so you put a little bit of voltage, a little bit of charge accumulates. You put more voltage, more charge accumulates, and so on. Okay, and what I tried to do here is just basically draw a simple circuit where I had this voltage which is pushing the charges onto the capacitor. Okay, and in the tradition of following positive current, the positive battery will push positives over here. The negative will, pull positives off of there, and you'll have negatives down there like that. Okay, so basically the side of the capacitor which is hooked up to the positive part of the battery acquires positive charge, and the part of the capacitor which is hooked up to the negative side of the battery acquires negative charge. Okay. Now, what's going on here is basically your battery is doing the pushing. You might ask the question, why can't it just keep pushing more and more and more and more charges on there? And the answer is it can't. Okay, so let's just think here what happens as you keep pushing electrons on. So what I have here is, remember, it's the electrons that are flowing. Okay, so what I have here is I'm trying to draw, like this one plate here, and we'll see in a minute that capacitors are often made out of two parallel metal plates. Okay, and what you have here is basically a wire hooked up to one plate, and then here's another plate, and there's a wire off of it. And the battery pushes one electron onto the negative plate. Okay, so great, there's an extra electron on that negative plate. What does that extra negative electron do? Well, that negative electron through the electric field will actually push on the electrons on the other side of the plate, on the other plate. Okay, so these other plates here, the positive plate, feels that extra negative from the negative plate, and it goes, I don't like that negative there. The negatives on the positive plate, they want to get away. And then there's this battery that says, hey, I'm accepting negatives. So guess what? The negative accumulates onto the negative plate, and a negative from the positive plate leaves, leaving behind a hole. And a hole is basically a positive. Okay, so we get something like this. Okay, so at this point we have that negative that was pushed on, and the negative that was pushed off by the negative that was pushed on the other side, and that leaving behind a hole. So we have a negative over here and a positive here. And the battery says, you know what? I still got more energy to do this. I still have more push to do this. So it pushes another negative on there. Okay, and on the positive plate, a negative there goes, well, I don't like this negative that's nearby me. I'm going to run away, and it leaves behind another positive. And it just keeps doing that. And so more and more negatives accumulate on the negative plate, more and more positives accumulate on the positive plate. But the thing is that now the negatives on the negative plate are crowded, and they don't like being near the negatives on the negative plate, okay? And the positives on the positive plate, they don't like it either, okay? And so they're saying, the positive is saying, look, we don't want to get rid of any more of our negatives. And so the battery keeps, as it keeps pushing charge on, the battery finds it harder and harder and harder to push more and more electrons onto the negative and to pull more and more electrons off of the positive. Eventually, at some point, it's the capacitor is saturated, and so for a particular voltage, you only get so much charge built up on that plate. Okay, now I think you can already imagine that the bigger the plates are, the more the plates can accommodate charge, and so the easier it is, the more charge you get for the same amount of push. And that's in fact the case. So what happens here is the amount of capacitance is going to be a measure of how much charge you can get per volt. So here's the definition of capacitance. Capacitance is how much charge will accumulate on the plate for every volt that you apply. Okay, you can think of this as the definition of capacitance, or like that. All right. So what is a big capacitor? A big capacitor would be one that would accumulate a lot of charge for just a little bit of push. Okay, so you don't need that much push. Small battery will be able to push lots and lots of charge because the capacitor has the capacitance to accept a lot of charge. Okay, so if you can accept a lot of charge for very little voltage, you have a very big capacitor. Conversely, if you have to really force those electrons on and then you only get a few, so you only get a small Q for very big voltage, for a very big push, that's a small capacitance. Okay, so there you go. There's the definition of capacitance. And I kind of introduced this in the sense of two parallel plates. But guess what also has capacitance? A cell membrane, because it has two sides. Okay, and cell membranes will use proteins, and I don't know the biochemistry of this, but these proteins, what they'll do is they'll actually actively pump sodium ions across the membrane and create kind of like a positive side to the membrane and a negative side to the membrane. It's kind of like a capacitor. Okay, so let's go on here. So next thing before we could do problems with this is what are the units of capacitance? So the units of capacitance are the units of charge divided by the units of volts. The units of charge are coulombs. The units of volts of voltage are volts. And a coulomb per volt is called a farad. Okay, named after a famous physicist, Michael Faraday. All right, and you'll actually see what he did with magnetism later in the course. Okay, so it's a coulomb per volt is a farad. Now, at this point, I have to sort of alert you to a possible confusion that comes up, there's two C's in here, okay? There's the one C, which is the symbol that refers to capacitance, okay? And then there's another C, which refers to the unit, which are coulombs, all right? And I don't know, I mean, physics has run out of symbols long ago, and so they've recycled them. It's kind of awful to recycle the same symbol in the same formula, so this kind of sucks, but there it is, okay? So in this equation here, this C is capacitance. So it's a symbol which represents this property of matter, which is its ability to accumulate charge per volt, okay? This C here is a Coulomb, which is the unit of charge. Well, is a unit of charge, okay? So I don't know what to say. I mean, just don't confuse the two, all right? All right, great. So let's try to understand the physics of capacitors a little bit better. Nothing as complicated as a cell membrane. Let's build the simplest possible capacitor so we have some idea of like how you can build a device which is capable of accumulating charge when a voltage is applied. And usually this is done by using parallel plates. Okay, and so you've got these parallel plates. And in the lab, you've actually seen some well, you didn't see them because we didn't do the labs physically together, but there were some capacitors which were like these little circular domes, which were ceramic. And that's actually ceramic around the parallel plates which are inside. And then there are like these two wires coming out of them. Okay, the ceramic, so the circular thing are basically these two little circular plates which are very, very close to one another. Okay, and so that's what I'm trying to indicate in this diagram right here. And we're looking at this kind of like on the side. Okay, so what you're seeing here on this side, this right here, is one metal plate. Okay, because you're looking at the side, you just see kind of a line there like this. Okay, but it's a plate. Okay, and we have another plate on the other side. They're like that. So they're the two parallel plates. And in the middle, you put some material, which is known as a dielectric, which does not conduct electricity. If it conduct, like you can't use metal in there, like copper. If you put copper in there, well then, you know, the electricity will just flow right through it and it will not act as a capacitor. You have to use something in there which is an insulator. An insulator is basically something which just does not allow electricity to conduct from one side to the other. Okay, and so this dielectric material has two properties. One is that it doesn't conduct electricity, and the other thing is that it enhances the capacitance of the capacitor. Now, how it does that at the microscopic level, I don't want to get into the details, but basically the atoms and molecules get polarized, and it's in that polarization of the atoms and molecules. Okay, you know, like an atom has the electrons on the outside and a proton in the middle. The electrons kind of get pulled towards the positive side of the plate. The nucleus gets pulled towards the positive side so that the electrons themselves have kind of a positive and negative side to them. So each little electron acts like a little bit of a capacitor, and that enhances the entire capacitance of the entire device. Okay, and these two plates, they have area A. Each one individually has area A. Okay, it's not the total area of both of them added together. It's the area of one of them is A, and the area of the second one is also A. Okay, and they are a distance d apart. Okay, and without proving to you why this equation holds, it's not that hard to prove, but I'm not going to do it. It's basically the capacitance of parallel plates is equal to the area of the capacitors divided by the distance between them, multiplied by this epsilon naught, which is a constant of nature, which I'll describe in just a second, and K, which is the dielectric constant, is purely a property of the material there. Okay, let's talk about the A and the D first. All right, remember what a capacitor does. A capacitor basically accumulates charge. The bigger the plates are, the more area there is to accumulate charge. Remember, the negatives don't like being near one another. So if you create a big area here, on this plate here, say that's the negative plate, you create a big area, you're giving more space to those electrons to spread out, and they're happier being there. All right, and so the bigger the area, the bigger the capacitance, and you can see that over in the formula because A is on top. You double A, you're going to double the capacitance. The D, however, is in the denominator. That means that the smaller D is, the bigger C is. And you go, well, why is that the case? Well, remember, what is it that pushes the electrons off of the one plate? The two plates, they interact with one another by an electric field. And the thing is that if there's a negative on the one side, it kind of pushes the negative off of the other side. Well, if the two plates are far apart, the electric field is kind of weak, between them. And so the further the plates are apart, the less one electron on one plate tends to push off an electron off of the other plate. If they're really close together, then that one electron on the one plate, it's influencing those electrons on the other plate quite a bit. And they're going, no, you get away from me, get away. And so the closer the two plates are, the more the one electron on the one plate will, the more the charge on the one plate will push the charge off of the other plate. And so it enhances the capacitance. So the closer the two plates are to one another, the bigger the capacitance. K, it's just a property of the material. It just says, how much is this, how polarizable is this material so that it enhances the capacitance. Okay, so there's some materials that do a really good job, like certain types of glass will enhance it by, like in my example in a minute, it'll enhance it by 14.5 times. Okay, so that's quite an enhancement of the capacitance. And then there's this mysterious epsilon naught there, like that. Okay, so that's the Greek letter epsilon naught. The reason there's a little naught there is because this is a property of empty space or free space. Okay, it's actually called the permittivity of free space. There it is there, and it's got this value 8.854 times 10 to the minus 12 farads per meter. Okay, those are the units you need there to make sure that everything works out, because see, A is in meters squared, M is in meters, K is just a number, like it's just an integer, or not an integer, but it's just like a dimensionless number. Okay, so it's 1 for a vacuum and bigger than 1 for some material. So to make all the units work out, you have to have that epsilon naught is in farads per meter. It's called the permittivity of free space. It's the ability of free space to maintain an electric field. Okay, and this is going to become a very interesting number later, after I do magnetism, because it turns out that the ability of free space to maintain an electric field and the ability of free space to maintain a magnetic field together, those two together actually produce electromagnetic waves. We've studied wave phenomena, and you know that in wave phenomena, the speed of waves, like on a string, goes as the square root of the tension divided by the linear mass density. You're going to see that this permittivity of free space is kind of like the tension of space with respect to electric fields. It's really quite fascinating, but that's, in the future. Okay, so there it is. And you go, well, this business of electric fields in free space, isn't that actually coming out of Coulomb's law? And the answer is yes. This is Coulomb's constant in disguise. Okay, so actually this constant here is basically Coulomb's constant. Remember, Coulomb's constant was in F is equal to K Q1 Q2 over R squared. There was that capital K. Capital K was called Coulomb's constant, and it was equal to 8.99 times 10 to the 9 newtons meters squared per Coulomb squared. That turns out to be related to epsilon naught by this equation here. So Coulomb's constant is 1 over 4 pi epsilon naught. And you go, where's this 4 pi coming from? I don't want to get into that. It's Gauss's law. But okay, but there's a 4 pi there. They're really the same constant in disguise. Okay, they're really the same constant in disguise. I could have not introduced epsilon naught at all and just rewritten that previous formula in terms of Coulomb's constant. And it totally makes sense, because after all, what's doing the pushing of the charges against one another on these parallel plates? It's Coulomb's law, okay, in the electric field, and there is coming out of Coulomb's law. So you would expect Coulomb's law to appear in the equation for the capacitance. So there it is. All right, guys, so it's time to do our first problem. And we're going to make a capacitor out of 2 metal plates, which are 3 centimeters, okay, by half a meter long. All right, so this is a kind of a metal strip like this. All right, and they're going to be held apart. The distance between one another is going to be 1.5 millimeters. So that's how far apart they are from one another. And we're going to put between the two, we're going to put glass. Okay, and this glass is going to have a dielectric of 14.5. By the way, capacitors, like physical ones that you see in the lab, they come in 2 shapes. One is kind of like a disc, like this. Okay. Say a flat disc like that. But another one are like cylinders. And you go, well, what are the cylinders? What they actually do is they make these really long capacitors like this, and then they roll them up. Okay, so it's kind of like a spiral in there, because how else are you going to get something, a bunch of parallel plates, with a lot of area into one short volume? And the answer is you curl them up. Okay, but that's just a bit of an aside. So the metal plates here are 3 centimeters by 50 centimeters, and they're held together, they're held apart from one another, very close, 1.5 millimeters apart, and we're going to put glass between them, and this is a special glass which has a dielectric of 14.5. Value 14%. There are no units. It's dimensionless. So what's the capacitance? Well, let's start off. We're going to need the area of the plates from that formula, and that's 3 centimeters by 50 centimeters. Okay, length times width. Convert to meters, so that's 0.03 meters times 0.5 meters gives you 0.015 meters squared. There's the area. The distance between the two plates is 1.5 millimeters, but convert to meters, and so a millimeter is a thousandth of a meter, so 10 to the minus 3. All right, and now we're just ready to plug in to the formula. And so here we go. We've got that C is equal to K, which is 14.5. Here's that mysterious epsilon naught, 8.85 times 10 to the minus 12 farads per meter. The area of the plates is 0.015 meters squared. The distance between the two plates is 1.5 times 10 to the minus 3 meters. Notice a meter squared on top, a meter on the bottom. That'll cancel that meter there, leaving just farad as the unit. Okay, and the rest of this is just some simple arithmetic, so I'm not going to go through the details, but you get 1.28 times 10 to the minus 9 farads. Okay, and 10 to the minus 9, that's a billionth, that's a nano, so 1.28 nanofarads. And you go, geez, this isn't exactly small. This is like 3 centimeters by 50 centimeters, so it's like half a meter. And you can imagine rolling it up. This would be a fairly good size capacitor, and you're only getting nanofarads. And that's right. A farad is actually a very big unit, okay? Typical size capacitance in the lab are usually going to be nanofarads or microfarads, okay? And micro, remember, is millionths, or 10 to the minus 6. Nano is 10 to the minus 9, okay? So you're looking at, a farad being a really, really big number. Let's think why. A farad is going to be 1 coulomb of charge accumulating for every volt. A coulomb, you remember, is big. In a lab, you're working in millicoulombs, and now we're talking a coulomb, which is a million times bigger. And a volt is really small. Okay, you can easily produce hundreds of volts in a lab, even thousands of volts in the lab. Okay, so you've got a very, very big unit divided by a very, very small unit, and so big divided by small, it gives you something which is very big. So a farad is very big. Again, typical nanofarads or microfarads. A millifarad is already huge. It's just huge. I don't think I've ever seen a millifarad capacitor in my life, or at least I don't know, in the electronics I've done, but there it is. Okay, so there it is. Let's continue here. Finish off this topic. So how much charge accumulates on that 1.28 nanofarad? I'm sorry, guys, I put a C there. That should have been an F. Okay, so this is 1.28 nanofarad capacitor if we apply 1,000 volts. Okay, so we have that 1.28 nanofarad capacitor, and we're going to apply 1,000 volts to it. How much is accumulated? And I really blew it here, guys. I put the C there again. Okay, that should be nanofarads. All right, so the definition of capacitor is C is equal to Q divided by V, and that rearrange that, the charge accumulated is just C times V. C is 1.28 nanofarads. Multiply that by 1,000 volts. Okay, now a volt times a farad, that's a coulomb. So this is correct here, but that C should be an F. Again, I apologize. Okay, and nano times 1,000. 1,000 times 10 to the minus 9 is 10 to the minus 6. So 1,000 nanos is a micro, and that gives you 1.28 microcoulombs. So basically, if we take that capacitor that we built, okay, which gave us a 1.28 nanofarad capacitance, and we apply 1,000 volts, which is doable in the lab, you're just going to accumulate 1.28 microcoulombs. Okay, and if you took those two, like if you put probes on both, or wires on both ends, and you touch them, you would definitely see a spark. Okay, this is not a trivial amount of charge. Okay, so this is a fair amount of charge. Okay, so there you go. All right. There's the general theory of capacitors. Now, just like resistors can be in series and parallel, capacitors can be in series and parallel. And again, think about this in terms of like some electronic properties of say biological material. Okay, you could have like one membrane accumulating so much charge and another membrane accumulating so much charge. They could either be in series or in parallel to one another. It depends. Okay, so don't think about this as just being limited. This physics is not just limited to stuff that you would see inside of an electronics lab. All right, so let's start off here, but we're actually going to start with the parallel. Okay, so we have here two capacitors in parallel. Here's our battery with voltage V. Here's capacitor C1. Here's capacitor C2. Okay, and they're in parallel to one another. Okay, so that means that the voltage across C1 and the voltage across C2, they're the same. Remember, in parallel, the voltage drops are the same. It's the currents that split. But currents are not that interesting with raw capacitors, okay? And so there are going to be currents as they charge up, but they're going to be very short-lived, transient currents, okay? So this isn't going to be something like with Ohm's law where we're talking about currents. Here, the three things that are really of interest are voltage, capacitance, and the accumulated charge, okay? You could think of that as the equivalent of Ohm's law, but for capacitors. All right, so V, it's the same across C1 and it's the same across C2. All right, so now we can say, all right, so the C's are the same. What's the charge accumulated on C1? Well, the charge accumulated on C1 is Q1, and Q1 is going to equal C1 times V, coming out of the definition of capacitance. And the charge accumulated on C2, Q2, that's going to equal C2 times V. But the V's are the same because the voltage drops across both of them are the same. So what's the total charge accumulated? Well, the total charge accumulated, we can call it Q equivalent. That's going to be the sum of the two charges, the sum of the charge accumulated on C1 and the charge accumulated on C2. But if we take this formula here and we plug it in, we're going to get C1V1 plus C2V2. We can factor out the V, so we get C1 plus C2 times V is equal to the effective capacitance times V. You divide out the V and you find that the effective capacitance is just C1 plus C2. Okay, so whenever you have capacitors in parallel, their capacitance add. Okay, so two capacitors in parallel, C1 and C2, the equivalent capacitance is C1 plus C2. Great. Okay, so what's next? Series. Here we go. We've got C1 and C2. Okay, they're in series. All right, and now the voltage across both of them is not the same. The voltage across the voltage across each one of them is not the same. The voltage across both of them is V, but the voltage across C1 we can call it V1, and the voltage across C2 we can call it V2, and the total V is going to equal C1 plus C2. Okay, there's one other thing you got to know about though, and that is the charge on C1 comes from C2. And you go, wait a minute, there's a battery there. I know, but that middle segment in there, see this middle segment in there, that's isolated. So it's not like there can be charge on C1 that didn't come from C2. And I actually try to draw that in my next diagram. Okay, so suppose that this is the negative plate of C2. Well, the negative plate is going to push electrons off of the positive plate of C2 and push them onto the negative plate of C1. For every electron that gets onto C1, it came from C2. And therefore, the charge on C1 must equal the charge on C2. So let me say that again. That electron that got onto C1, where did it come from? It came from C2. So every electron that's on C1's negative plate came from the positive plate of C2, so the charges must be the same. Okay, so that's kind of a little bit subtle, but basically the charge that accumulates on C1 and the charge that accumulates on C2, they're identical. Okay, so Q here is the same for throughout. All right, and so now we have that the charge that accumulated on both C1 and C2, we can just call that Q because it's the same. The charge accumulated on C1, you can write as C1 times V1, which is the potential across C1. And the charge that accumulated on C2, that's just C2 times V2. And C1 and C2, they're not the same because why? Well, because the potential drops get split now. Okay, and so the total potential drop, V, has to be the potential drop across C1 plus the drop across C2. So V is equal to C1. So V is equal to V1 plus V2. If we just take these and rearrange for V1 and V2 and substitute into this, we get that Q over the effective capacitance is Q over C1 plus Q over C2. It's all the same Q's. because Q on C1 is the same on Q on C2. It would be the same Q on the effective capacitance if you were to replace the two with just one capacitor. And so if you divide out the Q's, you find that 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. And so in series, when you hook up capacitors in series, it's the reciprocals that add. Okay. In parallel, they just add. In series, it's the reciprocals that add. Okay. And so there you go. There you have it. Now, at this point, you're going, this is the opposite of what we had for resistors. That's right. So don't confuse the two. With resistors, when they're in series, their resistances add. But when they're in parallel, their reciprocals add. For capacitors, it's the other way around. Okay. For capacitors, when they're in series, it's the reciprocals that add. But when they're in parallel, that it's just the capacitances that add. Okay, so don't get confused. This sometimes causes confusion, but it shouldn't. Okay, it shouldn't. It's just that they work opposite one another. All right. And so let's do a problem. Nothing very complicated. So rather than having 4 capacitors, we had 4 resistors before. I just thought I'd drop it down, drop the difficulty down a level. Now we only have 3 capacitors. Okay, and in part A, I'm going to ask you for what the effective capacitance is of the whole circuit. And in part B, I'm going to ask you for the potential drop and the charge accumulated on each capacitor. Okay, and so here we go. So I didn't draw the whole circuit. Basically, I didn't draw the battery in there, but this is 10 volts over here, and that's 0 volts there. And we proceed the same way as we did with resistors. We reduce a pair at a time. Okay, and we have to identify, do you see anything which is in series, purely in series or purely in parallel? Well, you could say C1 and C2, not really. They're not in series because there's that split in there. I think it's pretty obvious. You first have to reduce C2 and C3. They are purely in parallel with one another. Okay, so when capacitors are in parallel, you add. So the effective capacitance of 3 is C2 plus C3. And C2, I made that out to be 4 microfarads, and C3, I made it to be 5 microfarads. So 4 plus 5 microfarads is 9 microfarads, okay? And so the effective resistance of C2 and C3 is 9 microfarads, okay? The circuit now reduces to this, where you had C1 in series now with C23, and C1, I forget what that was. C1 was 3, okay? So C1 was 3 microfarads, and this one we just found was 9 microfarads. When they're in series, what do? You add the reciprocals. So here we go. So the effective resistance of the whole circuit, that's the capacitance of 1, 2, and 3, is equal to 1 over C1 plus 1 over C23. And that's 1 over 3 plus 1 over 9, and that turns out to be C123 is 2.25 microfarads. There we go. We've answered the first question. What is the effective capacitance of the entire circuit? And the effective capacitance of the entire circuit is 2.25 microfarads. Great. Next question. How much charge accumulates on each capacitor if we apply 10 volts? Okay, and I could have also asked there, what's the potential drop across each of them? And that'll come out as we do this as well. Okay, so I didn't ask it there, but I actually do put it in the summary later. All right, let's do it. So just like with resistors, we work backwards. Okay, and so the first question is, if you look at the circuit, if you look at the, this combined circuit here, okay, what we don't know so far is what is the total charge accumulated. We know the effective capacitance of the entire circuit. We know the effective voltage across the entire circuit, but we don't know the charge that's accumulated by the entire circuit. And so basically Q is equal to CV, okay, which is the definition of capacitance. So Q123, that's the charge accumulated by all of the capacitors together. That's going to equal the equivalent capacitance of all of them, 1, 2, 3, multiplied by V, the voltage across all of them. Well, we just found the equivalent of all of them. That's 2.25 microfarads multiplied by 10 volts. And it says that basically all of the three capacitors together accumulate 22.5 microcoulombs. Okay, so there's the total accumulated charge by the circuit. Okay, and now we can actually ask, what is the potential drop across C1 and the potential drop across C23? Okay, so we're working backwards here. We're basically taking the circuit and breaking it up into the two, like this. Okay, and so there's a potential drop across C1, we'll call that V1, and there's a potential drop across C23, we'll call that V23. V1 plus V23 must equal 10 volts because the potential drop across each one adds, and so we can now find the potential drop across C1. Well, again, using Q is equal to CV, we know that the charge accumulated on C1, because it's in parallel with C23, it's the same. So both C1 and C23 accumulate 22.5 microcoulombs. They're in series. In series, the charges on both capacitors are the same. We just said that, okay? So we know that the charge on C1 is the same as the charge on C123. And we know that C1 is 3 microfarads, and we don't know V1, but now we can solve for V1. So just rearranging that formula, you get that V1 is going to be the total charge accumulated divided by C1. That's 22.5 microcoulombs divided by 3 gives you 7.5 volts. Okay, so the voltage drop across C1 is 7.5 volts. All right. Similarly, the potential drop across C23, that's going to be V23 is going to be the charge accumulated on C23. Remember, the charge accumulated on C1 and the charge accumulated on C23, they're in series. It's the same. It's 22.5 microcoulombs. So Q is 22.5 microcoulombs. The capacitance is 9 microcoulombs. The micros just cancel. That makes life easy. So we get 22.5 divided by 9, which is 2.5 volts. Okay, so the drop across C1 is 7.5. The drop across 23 is 2.5. 7.5 plus 2.5 is 10, and that's what you expect, okay? Because the total potential drop has to be equal to the potential that's being applied by the battery, okay? So again, across C1, it's 7.5. Across C23, it's 2.5. 7.5 plus 2.5 is 10. Okay, so there's our check. I'm going a little bit faster than I did with the resistor. It's the same procedure as with the resistor, but now we're thinking in terms of capacitance, voltage, and charge. All right, and now we go back another step. This is our last step, and just isolate the C23 and break them apart. Okay, so C23 comes out of C2 and C3, which were two parallel capacitors like this. The voltage drop across both of them, that's just 2.5, because we already had the voltage drop of 7.5 across C1, and now C23 had the 2.5, so it's 2.5. So we have the potential drop across C2 is 2.5, and the potential drop across C3 is 2.5. They're in parallel, and when you're in parallel, the potential drops are the same across both components. So it's across C2, it's 2.5. Across C3, it's 2.5. And now we can figure out the accumulated charge on C2 and the accumulated charge on C3, because you have the potential, you have the capacitance, and you can get the charge on each one of them. Okay. And for the charge, you can just use Q is equal to CV. So for Q2, that's C2 times V23. Why 23? Because the potential drop across either 2 or 3 is 2.5. So C2 was 4 microfarads, and C23 was 2.5. Multiply the two together, and you get 10 microcoulombs. So C2 acquires 10 microcoulombs charge. Same thing for C3. C3 accumulates a charge Q3. Q3 is C3 times V23. That's 5 times 2.5, and you get 12.5 microcoulombs. Remember that the charge accumulated by C23 has to be 22.5. So if you add 10 plus 12.5, you get the total accumulated charge of 22.5 as expected. Okay, so it works out. And so we can summarize everything. If you go back over this, you can summarize everything. And the 3 microcoulomb had a potential drop of 7.5 volts across it, and it accumulated 22.5 microcoulombs of charge. The 4 microfarad had a potential drop of 2.5 volts, and it accumulated 10 microcoulombs. The 5 microfarad had a voltage drop across it of 2.5, and it accumulated 12.5 microcoulombs. Okay, so same procedure, so I should say similar procedure to the when you have a bunch of resistors in series and parallel, but now the triad is going to be capacitance, voltage, and charge accumulated. Okay, and what you do is as you work backwards, you ask, what do I know? Do I know the capacitance? Do I know the voltage? Then I don't know the charge. Let me find that. Or conversely, you might know the charge. When they're in series, you'll know the charge, and you might know the voltage, but you don't know the capacitance. Or sorry, you'll know the charge, you'll know the capacitance, but you don't know the voltage. And so, working this way through it, you'll be able to find everything that you're asked to find. All right. Last circuit that we're going to study in electricity, and the next topic will be magnetism. These are known as RC circuits. So what happens if you put a resistor and a capacitor together with a battery? So this is an interesting circuit. This is actually turns out to be a timing circuit. So what happens is you have this capacitor and this battery, and the battery wants to charge up the capacitor. And it does that by just pushing so many electrons onto the capacitor. Now the capacitor can't take an infinite amount of charge, so what it does is just charges up to a certain amount and then it stops. In a perfect world where there's no resistance in the wire and the battery can deliver as many electrons as necessary, okay, the current will be infinite for a very, very short excuse me, for a very short moment, and the capacitor will charge up instantly and then we're done. Okay, well, that obviously doesn't happen in the real world because everything has a little bit of resistance. There's always a little bit of resistance to the current. You're not going to have these infinite currents, and so your capacitor can't possibly charge up instantly. It'll take some time to charge up. And here's the thing: the more resistance there is in the circuit, the slower the current, the longer it takes for the capacitor to charge up. And so you have a timing circuit. Basically, if you want to go from a certain amount of charge to a certain amount of charge, it doesn't happen instantly. It happens over a certain period of time, and you can actually control that time. What limits how long it takes for that capacitor to charge up? Well, two things. Okay, it's actually not the battery size, interestingly enough. That'll just determine what the final charge is. Okay, it doesn't determine how fast or the rate at which it charges up. Two things. One is how big is the capacitor. The bigger the capacitor, the more charge it can accumulate, and the longer it'll take to accumulate that charge for a given resistor, because the resistor is going to say, no, there's so much current, and the capacitor is huge, so it says, just keep sending it, so it can take a long time to charge up. So the bigger the capacitance, the longer it takes to charge up. But also, the bigger the resistor, the longer it takes to charge up. Because for a given size capacitor, if the resistor is really big, it limits that current, and then it takes a long time as that current just very slowly trickles through that resistor and accumulates on the capacitor. So what determines how long it takes the capacitor to charge up are two things: the size of the capacitor, and the size of the resistor. And this leads us to this characteristic time of the circuit. It's called the time constant. And I say characteristic because it characterizes this rate at which a capacitor will charge up. And the time constant is actually a product of two things. It's a product of the resistance times the capacitance. The bigger the resistor, the longer it'll take to charge up. The bigger the capacitor, the longer it'll take to charge up. The bigger both of them are, it's the product of the two, which will determine how long it takes to charge up. This is known as the time constant. Tau is the time constant for an RC circuit. Okay, I'll show you in a minute that if you actually multiply ohms times farads, you're going to get seconds. Not something you would expect. But if you take ohms, which are the units of resistor in MKS, and you take farads, which are the units of capacitance in MKS, you take an ohm, multiply it by a farad, it's equal to 1 second. Okay, which is kind of interesting. All right, so what's this RC circuit look like? Here it is. I've drawn both the charging up and the discharging circuit, because a capacitor can either charge up through a resistor or it can actually discharge through a resistor. And so what do we have here? Well, we've got a new component in here. We've got our battery. We know what that is. We've got a resistor. We know what that is. Got a capacitor. We know what that is. And then we've got this switch S. And this switch S can be in one of two positions. Switch S can be in position number one, in which case just ignore this entire line there. And the battery, what does it do? It just flows through here, it flows through here, it flows through the resistor, and it pushes charge onto the capacitor. That's the capacitor charging up. Okay, great. After a while, if you wait long enough, the capacitor is charged up and the battery just can't push any more charge on there. That's it. Capacitor is charged up. At that point, you can flip the switch from position 1 to position 2. When it's in position 2 here, just ignore the battery. It's out of the circuit. Now, all you have is the R and the C in the circuit like that. Okay, and guess what the capacitor does? The capacitor says, oh, now my electrons from one side, they can flow through the resistor to the other side and the capacitor discharges. So when the switch is in position 2, the capacitor is discharging. When the switch is in position 1, the capacitor is charging. Okay, so there you go. There's an RC circuit in both possible cases of charging up and discharging. Let's take a look first at what the graph looks like when the capacitor is charging up. Okay, and what we're going to plot is, you can plot several things. You can plot the potential across the capacitor. You can actually plot the current through the circuit or whatever. Probably the most intuitive is to plot the charge on the capacitor. Okay, if you flip the switch into position 1 at t equals 0 and there's no initial charge on the capacitor, the initial charge starts here at t equals 0 at 0. Okay, so there's no charge on the capacitor at t equals 0. All right, but that's not going to last for long, because the battery now says, yeah, I know there's a resistor there, but I can push charge on. I can push charge on. And so it starts to push charge on. And so as time goes on, the horizontal axis here is time, the vertical axis is charge. The capacitor begins to charge. It charges, it charges, it charges. But after a while, it can't charge anymore. And so it actually reaches the maximum, and I call that maximum Q naught. I guess I could have called it Q max, but I called it Q naught. Okay, so Q naught is the maximum amount of charge that's going to accumulate on this capacitor, and it's just going to charge up like that. And you could see that the actual charge Q approaches this dashed line, but it never actually gets there. It just gets infinitesimally close to it. This is what in math is known as an asymptote. But after about 5 time constants, most people say, yeah, it's so close that whatever little difference there is, it's absolutely negligible. You're not going to even be able to measure it. Okay, so it basically charges up. At first, it charges up fast, and then the rate at which it charges up slows down, but it continues to charge up until finally you can't get any more charge on it. So this is the characteristic curve for the capacitor charging up. That's when you have the switch in position 1. Okay, now what? Well, what's the formula for that look like? Well, the formula, Q as a function of time, it basically exponentially approaches Q naught. And Q naught, what's that going to equal? That's just going to equal C, the capacitance, times V. That, in fact, is exactly the formula I gave you earlier. C is equal to Q over V, only now it doesn't charge up right away. So it doesn't reach the full charge CV right away. It takes some time, but eventually it'll get there. Eventually it will charge up to Q naught is equal to CV. Okay, so no difference for that part of the formula. Now it's stretched out over time. So Q as a function of time is going to equal that Q naught, that maximum, multiplied by this function here, 1 minus E, that's Euler's constant, e to the minus t over tau. Okay, now that E on your calculator, you're going to have to figure out how that works. Every calculator is a little different, but basically that's Euler's constant is like 2.728, blah, 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 blah. It's one of these non-repeating, non-terminating decimals. Okay, and so this is e to the minus t, and that's your time in seconds divided by tau, and that is that time constant. Okay, so this looks like a complicated formula, but it's not that bad. It's not that bad. Okay, let's take a look at how that exponential works. So if you start at t equals 0, let me just scroll down just a little bit more. Okay, if you start off at t equals 0, what you're going to do is, you see that e to the minus t over tau? You're going to put in 0 for time, t. Okay, well, 0 divided by tau is 0. Tau is not 0. Okay, so it's just some number. So 0 divided by some number is 0. So e to the 0 is 1. You take any number and you raise it to the exponent 0 is equal to 1, and e is no different. So e to the 0 is 1. Now, if you have 1 there, and then this e to the minus 0 is 1, 1 minus 1 is 0, you start off at q equals 0. So at t equals 0, there's no charge on the capacitor. And that's exactly what you saw on the graph here. Okay, at t equals 0, the charge is 0. Okay, I guess I should have maybe labeled here that that's going to be q equals 0, but I think it's kind of obvious. All right, okay, great. So at t equals 0, you have no charge. What happens after you wait time one time constant. So when t is equal to tau, now take that little t in there and replace it with tau. You get e to the minus tau over tau. Tau divided by tau is 1, so that's e to the minus 1, which if you do that on your calculator, you get 0.368. And that means if you wait one time constant, your charge is at 63% of maximum. So it starts off at 0, and after one time constant, it's reached 63% of its maximum. Okay? Well, what if you wait two time constants? Well, now you're going to put in here e to the minus 2 over tau. Sorry, e to the minus 2 tau over tau. Okay, that's e to the minus 2. You work that out on your calculator and you're going to get 1.35. Now remember, over here, it's going to be 1 minus 0.35. Okay, and so actually you're going to get a bigger number. And by the time you're at 2 taus, Q is going to be 86%. And you do it again at 3 taus, you're at 95%, and so on. And so as t approaches infinity, as time gets longer and longer and longer into the future, e to the minus t over tau gets smaller and smaller and smaller. Here you can see e to the 0 was 1. E to the negative 1 was 0.368. E to the negative 2 was 0.135. E to the negative 3 is 0.050. Okay, e to the negative 4 will be even smaller. Try this on your calculator. Do e to the minus 10. Do e to the minus 20. Before you know it, it's 0. Okay, and 1 minus 0 is just 1. And so as t gets bigger and bigger and bigger, Q approaches Q naught, which is the maximum charge. And that's exactly what you're seeing in the graph. Okay, so there you go. There's a story of a capacitor charging up. It starts up charging fast at first, and then it slows down, but eventually it will max out, and it'll max out at Q naught, where Q naught is just equal to C, the capacitance, times V. All right, great. Now, what if you put the switch into position 2? Well, in position 2, if you recall, the capacitor just discharges through the resistor. So what happens there is you start off with some maximum charge, and as soon as you short out the RC circuit, the capacitor will start to discharge through the resistor, and eventually it'll go down to 0 charge. So there you start at the maximum and you go down to 0, and here we go. So here we go, we're starting at a maximum, and the curve will curve down, 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 and eventually at long times it'll get down to 0 charge on the capacitor. Now if you take a look at this and you say, well, what does that look like as a formula? It kind of looks like the previous one, but now you don't have 1 minus e to the minus t over tau. Now you just have Q naught times e to the minus t over tau. Okay, and this is exponential decay. This is the situation where you're discharging, or in my diagram, when the switch is in position 2. Okay, so similar formula, and let's think about it in the same way. When t is equal to 0, if you put e to the 0 there, that's 1. 1 times Q naught is just Q naught, so Q starts off at Q naught. It starts off at its maximum charge. Okay. And then if you wait one time constant, e to the minus tau divided by tau, that's e to the minus 1, that's 0.368. So now, after one time constant, it has decayed down to 37% of its original charge. After two time constants, it's down to 14, and so on. So it decreases. And you'll notice that it actually starts off discharging faster, and then it discharges slower and slower and slower and slower. It'll eventually get down to 0, but you have to wait a long time. And you'll notice that as t becomes bigger and bigger and bigger, Q gets closer and closer and closer to 0 in that formula. Okay, I didn't write that down, but I think it's kind of obvious. All right, now we're ready for our problem. Okay, so here we go. A 35 microfarad capacitor discharges through a 500 kilo ohm resistor. Both of these are doable in the lab. 35 microfarads, that's a pretty big capacitor. That's about as big as you're going to get in any electronic component, like a computer. If you look inside computers, you'll see capacitors all over the motherboard. Okay, and 500 kilo ohms. That's a pretty hefty resistor, but very much something that you can get in the lab. And we're going to put them in series, the way you just saw in the diagram. And I want to know, how long does it take for the capacitor to discharge to 50% of its original charge? So I'm not even telling you what the original charge is or whatever. I'm just saying, look, it starts at some maximum charge, and I want to know how long until it gets to 50%? Maybe it starts at 1 microcoulomb, and I want to know how long does it take till it gets to half a microcoulomb. But it doesn't matter where it starts. It could start at 10 microcoulombs, and I want to know how long it takes to get to 5 microcoulombs. It's this fraction, the drop by 50%. That's the essential thing. Okay, so let's start off. The first thing you're going to need in all of these problems is you're going to have to find the time constant, tau. That's equal to RC. And so that's going to be 500 kilo ohms, but we got to work in the MKS, and the MKS units for resistance are ohms, not kilo ohms. So that's 500 times 10 to the 3 ohms, and the capacitor was 35 microfarads, and micro is 10 to the minus 6, so 35 times 10 to the minus 6 farads. And you multiply this out, and you get 17.5 seconds. At this point, you're going to ask, really, is an ohm times a farad equal to a second? And the answer is yes. So if you take a look here, remember what an ohm is. An ohm is a volt per amp. Okay, it's coming out of Ohm's law. Okay, and a farad, what's a farad? A farad is a coulomb per volt. All right, and it almost looks like we can multiply the two, but amps and coulombs, they have a relationship. An amp is a coulomb per second. And so we're actually going to write the amp down here as a coulomb per second. So the ohm is going to be a volt per coulomb per second. And a farad is a coulomb per volt, and you'll see that the volts will cancel, the coulombs will cancel, and the seconds, because they're in the denominator of the denominator, they come up into the numerator, and you get seconds, okay? So rather remarkable. You wouldn't have expected this, that if you take resistance, the units of resistance, and you multiply them by the units of capacitance, you actually get time. But you do, okay? And you can see that how that works out in the RC circuit. Okay, so anyhow, the time constant is 17.5 seconds. That means that a characteristic amount of time for this thing to decay is 17.5 seconds. And we're going to plug that into this formula. But you say, well, where do I use that 50%? Well, Q has to be 50% of Q naught. That means if you form the ratio Q over Q naught, that's 0.5. Okay, and so basically just divide Q divided by Q naught, that's 0.5, and that's got to equal the e to the minus t over tau. And so there we go. We've got 0.5 is equal to e to the minus t divided by 17.5. You're trying to solve for t. And at this point you go, well, how do I do that? Well, we actually saw something similar to this when we did decibels. Only there it was log base 10 and exponentiation base 10. Here it's log base e, also known as the natural log, and e, okay, for the exponentiation. And the way you do that is you have to undo the exponentiation, and the opposite of exponentiation is log. So if you take the natural log of both sides, you'll basically get the following, okay? And so natural log is written ln. So log base 10 is written log with a little 10 on the bottom there, but sometimes I just write log, and some calculators will just have log, meaning log base 10. Here ln is log, but log to the base of e, okay, Euler's number. And so we have natural log of 0.5, that's got to equal e to the minus t over 17.5. And you go, what did you just do there? What just happened? So take a look here. We're taking the natural log of both sides. So we have 0.5. And what's the natural log of both 0.5? Well, it's ln 0.5, you can do on your calculator. What happens when you do the natural log of the exponentiation? Well, they're opposites of one another. So if you exponentiate and then you log, it's like the log undoes the exponentiation. And so basically, taking the log of the exponent just pulls out the exponent here. So that's e to the minus t over 17.5. So the natural log of the 0.5 is just going to equal the exponent here, negative t over 17.5. Now, if you do the natural log of any number less than 1 is negative. So the natural log of 0.5 is going to be negative 0.693. That's going to equal negative t over 17.5. The negatives cancel. Multiply both sides by 17.5, and you get that 12.1 seconds. So whatever that capacitor was charged to, when you flip the switch to position 2, it starts to discharge. If you were watching this on the oscilloscope, it would start at that top charge, and it would take 12.1 seconds before it gets to half of that charge. And on the oscilloscope, you can actually have the settings so that it triggers on, when it reaches that particular charge, and you would actually see that characteristic shape on the oscilloscope. Okay, now I should say something. Oscilloscopes technically only measure voltages, and so you wouldn't be measuring the charge on the capacitor, but you would be measuring the voltage drop across the capacitor, and the voltage drop across the capacitor and the capacitance will tell you what the charge is on the capacitor. Okay, so there it is. that's the end of this lecture. Actually, this video, which is actually 3 lectures in the classroom. And let me just very briefly remind you of what we went over. We went over voltage, okay? We went over current. We went over resistance. We went over equivalent resistance if you have resistors in series and parallel. We went over capacitance. We went over capacitors in series and in parallel. They're equivalent. And then finally, we went over RC circuits. Okay, thank you.